Καλημέρα σας και ευχαριστώ για την πρόσκληση. Θα μιλήσω στα αγγλικά, θα δώσω την ομιλία στα αγγλικά, η οποία θα είναι γενικά μια στρατηγική πάνω στο AI και στο healthcare, όχι συγκεκριμένα πράγματα, όπως είναι μια πολύ καλή ομιλία μόλις τώρα. As presented before, I'm a professor of computer science in the Genome Center at UC Davis. I also wear another hat. AI institutes have been established about 2 years now in the United States. One of them is the AI for Next Generation Food Systems. It's a USDA NSF initiative. They funded us with $20 million to start with, and we're getting 15 to 20 million in terms of contracts and grants every year. And this is a collaboration between Cornell, Berkeley, UC Davis, UIUC, and other institutions. The focus of the Institute, with more than 60 faculty, is to improve human health through nutrition and generally improve the food systems through AI. Food systems, we see it as a continuum being from agricultural production and food breeding, molecular breeding, to processes, distribution, and nutrition, of course, for the consumer. My third hat is as a founder for different companies, two of them being Pipa LLC and Deus Ex Machina, which is a company that headquarters here in Thessaloniki, with about 60 to 70 employees. So let's talk about the perfect storm that we're witnessing in AI in general and AI in medicine more specifically. 350 plus AI-enabled medical devices approved by FDA, the Food and Drug Administration in the United States, which is a stark difference from what we had a few years ago. 11 billion being the market right now, and we're looking at about 40% of CAGR growth, with raising to 190 billion by 2030. At the same time, in a recent survey of 1,500 physicians practitioners, only 20% of them say that AI has changed the way they practice medicine. Of course, this has increased over the years. It used to be 11%, 15%, now 20%, and we see that trend actually going up. But there is a lot of issues about doubtfulness and trustworthiness, and many of those issues are for the right reasons. A brief history of what brought us here. So everything started about 80 years ago with neural networks and AI, artificial intelligence. But actually, about 10 years ago, in 2012, we witnessed an exponential jump in transformative technology, which is called deep learning. If you remember, there was about AlexNet and deep learning by Google, where they were able to recognize from many, we're talking about millions of images of cats, the cat face. Like the algorithm was able, without any training, figure out that, hey, there's an entity there. I don't know what it is, but it looks similar all over the place. So I will take it as separate. So it was able, for the first time, to recognize, without training, an entity. There was a lot of hype over the years, and I cannot, we need to acknowledge both for the good that it has done for AI in medicine, as well as the damage it has done, IBM Watson, which was a really visionary, controversial, and audacious attempt to bring AI in medicine. And knowing the whole history over the past 10 years of AI in IBM Watson, I can tell you the team is really good, especially in NLP. They're some of the forerunners and really pioneers in the field. At the same time, they oversold it. They brought it as the panacea and the solution to everything. And this created, it backfired, and it created an issue to anybody else who wanted actually to advance the field. Okay, so going forward, let's look at where AI can come in healthcare and medicine. Well, everywhere. These are some of the examples that you can see from wearable devices, from predictors, diagnostics, better care, quality of care, from more administrative tasks like billings, predictions of length of stay and mortality, so you have better treatment and better management, as well as clinical trials, finding new drugs and bioactives, as well as other more holistic approaches. When I say holistic approaches, and we're going to see what AI really means here, it's a different thing talking about a predictor, and it's a different thing talking about real AI, where it's not only a predictor, but it's an all-encompassing, overarching system that can make decisions, and it can make recommendations. And if you let it even actually have these actionable insights materialize, may that be a robotic movement, maybe that be part of a surgery, or may that be on what will happen for a patient. There is, and this list, what you see here is some of the different approaches that have been already published, and this is already 2 years old, the list. And you can see that there is a broad spectrum over all the different areas in medicine, from radiology and pathology, dermatology, ophthalmology, gastroenterology, and cardiology. And again, this is a small sample of what we have already. Now, most of them are retrospective studies, and this is something we need to discuss. The ones with the star are only prospective, so they're forward-looking. And this is one of the pain points that we have right now. It's easier and less realistic to get a data set from a hospital, things that have already been done, and create a predictor that has some kind of statistics, and they are the right statistics from a machine learning perspective, but maybe they are not the right ones if you want to be a practitioner. Maybe they are not correlating and connecting well to what would be useful for a physician. The vision is to integrate all these disparate sources of data coming from, as you see here, demographics and social and behavioral, all the down to microbiome and different genomics, medical histories, images, etc. Pass it through this magic box or black box, or maybe magic black box, and at the end having a virtual health guidance, you can imagine as the guardian angel of all of us. Well, again, this is the dream, this is the vision. We're not there yet, but we have done some amazing work towards this vision. Let's talk a little bit about AI. So what is AI exactly? So the backbone of AI in healthcare, I was thinking on how to have it at the right level of abstraction, and I came up with these different classes. So one is creating predictor. You want to predict when a disease will have its onset, if ever, on a particular individual. You want to predict the length of stay. You want to predict the probability of occurrence. And that would mean if it is continuous variables, that would be a regression. If it is non-continuous, binary, digital, it will be classification. Another application will be finding patterns in unknown data, the CAT paradigm that I just mentioned, where you're using clustering and dimensionality reductions. So imagine that you have a lot of types of data, and that can be n types of data, and you want to reduce the dimensionality to 2 only, right? So you can visualize, because we cannot really visualize n types of data and vectors in space. So that would be dimensionality reduction. Learning from other domains is a field that's called transfer learning. So maybe we have a lot of data from a specific disease, let's say IBS, irritable bowel syndrome, and we are learning, we are teaching AI on predicting the outcome there, what would be the best outcome, the best treatment. But we don't have, let's say, for ulcerative colitis. So what do? One is go and gather the data. That's a painstaking, slow, and difficult and expensive process. Of course, it has very good outcome if it's done properly. The other one is training on IBS, training on the data we have, and then somehow with the few data sets that we have, train on the new disease, which is ulcerative colitis. That is the focus of transfer learning. How do you do that efficiently? Learning optimally as you go is, we have some data, great, we have our patients. Well, where should I invest next so I will have the maximum bang for my buck? So if I have a specific budget, where should I do my next exploration? Where should I take my next sample? Learning from the environment and best actions, this is where true AI comes in. Everything before that was really machine learning. Advanced, shallow, deep, doesn't matter, but it was machine learning. Learning an environment and best actions is where you can make a recommendation system where all this come together in order to build a system level, a platform that uses techniques like reinforcement learning to learn the environment, learn the policies, learn the actions that is optimal. They are maximizing the cumulative reward. Not what will happen in the next step, but what will happen 5, 10 steps down the horizon. Now, all this now, they're being used in different fields, subfields of AI and machine learning. When you're dealing with images, we're talking about computer vision. When you're dealing about text and documents, we're talking about natural language processing. And when we're talking about general massive data sets, then we're talking about deep learning. Okay? So some of the challenges now, like what are the barriers? What stops us for this vision to materialize? So first of all is data availability. Even now, if you try to get some data sets that are out there published, they should be available to you. They are from taxpayers' money, most likely. You'll not be able to do it. You'll find a lot of problems. People will not want to separate from their data. That's one. The second is, even if they give it or they're deposited because the journals want that or because the funding agency mandates that, they're not going to be well standardized and interoperable. You will not be able to merge them together to create a compendium. A compendium will be a collection of all these data points, because these algorithms, when we're talking about AI, machine learning, and more even so, if we're talking about deep learning, they need massive amount of data. Just to give you an example, for machine learning training, you need hundreds of samples. For deep learning, we're talking about hundreds of thousands or millions of samples. So you need a lot of data. Without data, you don't have machine learning. Well, that is a problem a lot of the times out there, because if you look at the omics data, for example, a study that was published 2 years ago, omics data out there, about 80% of the data cannot be integrated. So we're talking about the same disease, we're talking about more or less the same experimental setting, the same types of data. You cannot integrate it. It's noise. So only 20% of that would be actually viable and useful. Statistical significance versus practical utility value. Again, I am an engineer. It's very easy for me to get metrics like p-values and AUCs and error curves and PRs and all this kind of stuff. And it will look beautifully in my PC, and I'll be so happy when I see these algorithms. But when I go to a team of physicians, when we're getting together, what really matters is what it does for the patients. And there we have what is called the AI chasm, like the barrier for communication, but also the barrier to connect to the final recipient, which is, again, the quality of care for our patients. Model explainability is another issue. It's a vibrant and very, very active area of research. Basically, when we're talking about deep learning or any kind of neural network type algorithm, it's a black box. You don't know what's happening in there. You have neurons, and you have inputs and outputs, a lot of neurons. It's as if you want to decipher our brain. Of course, it's much less complexity, but it's almost random connections with different activation function, meaning different functions there, different parameters. You cannot make sense. Okay, good. So is it enough for creating a predictor that will have 90% accuracy, for example? Don't you really want to know how it makes the predictions? Wouldn't you trust something much more, especially with the life of a person, if you know what's happening under the hood. So this is where explainability comes in. And if you see the field of explainability, explainable AI, this is what you see here is on top is model accuracy. And you see that deep learning is pretty accurate when you have the data, right? Imagine that we have all the conditions there already for us to train. And you're looking at the model interpretability being the x-axis. And you see that deep learning, although it's very good in terms of accuracy, you cannot interpret it. Again, imagine stacks, layers and layers of neurons with different functions that you don't know how they're connecting with the final outcome. You can go down, and if you go to more decision trees and rule-based learning, then you can see the rules. And yes, that is more interpretable, but it is not as powerful. So the field of machine learning is spending a lot of money and effort to make those black boxes, to open them up and make them white, right? Model bias is another issue that has emerged over the years. A lot of our training data, they have been biased because maybe we collect them here in Thessaloniki, and they represent the diversity of Thessaloniki. They don't represent the ethnic diversity of Greece or even Europe. Maybe it's more heavy on men versus women or of a different social group. And that creates biases because, again, all that machine learning and AI is finding associations in data. That's it. You have a variable here, you have another variable here. It finds the association between the two variables. It can be a complex association, but that's what it does. So the type of data that you put in would determine the generalization ability, how robust your predictor, your algorithm is in the general public. And we have seen that again and again, that's an issue. It's more difficult to see it in a chromosome or to see it in medical data. You can see it here. So if they trained an artistic deep learning where they were looking at making an image of a person, they were putting images of Black people, and you could see that they would turn white magically. And the reason is because, of course, the training set was mostly white, male people, persons. Again, we don't care so much about images of paintings, but when we're talking about whether a patient will, will take drug A or B, and you have been predisposing your algorithm on a totally different social group, you haven't personalized to that patient, that can be a problem. Another issue is regulatory, as you can imagine. This is a new field for agencies like FDA, Food and Drug Administration. They don't really know how to, they spend a lot of time and they're pretty smart about it, but because it's a new field, there's a lot to be done, a lot of hoops that people need to jump over. Security and privacy, obviously, and trustworthiness, hype versus real. Trustworthiness about the result that you're getting, as well as what can be done. Because it's very easy for people to show you nice images and tell you how great they are and how great their algorithms are, especially companies, right? Big players. But the reality is usually very far from what we have, what they show you. And we have already, the gap has closed already from what it was 5 years ago. But there is a long way ahead. A little bit about our work. Both in the university and the institute, as well as different companies that I'm part of, we have been using AI for more than 10 years now. I can tell you that the struggles that I had in 2012, we created a reinforcement learning from 1,500 patients in sepsis. We had a reinforcement learning algorithm that it was beating retrospectively 13% the different patient outcomes, the different decisions from physicians. And this was a team with about 14, 15 physicians together. When we went for funding in NIH, you should see the comments. It was like, this is the oracle from the 80s. It will never happen. AI will never be part of clinical decision-making, right? And people thought that we were crazy. Now, that was 2012, right? The world has changed. And what we see now, both the hype as well as the doubt will recede as we go forward. That's another case study that one of my company has completed together with partners. Well, I talked about the regulatory issues. So in 2016-17, we saw an opportunity there. There was a database with millions of cats and dogs from 1,900 clinics. We went there, we took the data, and we created a CKD predictor, chronic kidney disease predictor, that can predict up to 2 years beforehand. Now, this predictor, we deployed it with our partners, and it screens thousands of cats every day. And it has created, I'm not liberal to say the actual number, but you can imagine hundreds of millions per year for our clients. So this is the promise that we're talking about. Now, we were able to do that because A, we had great partners. Two, this is a not regulated as much as regulated field as in the medical field. What we're working right now, and this is my last slide, is figuring out what are the novel bioactives for different diseases and health states. So can we find from the millions of papers that have been published, 21 million papers plus, can we find from the raw data that's out there, like if you go for disease like diabetes, we have hundreds of thousands of samples of omics data, RNA-seq, transcriptomics, genomics, you have proteomics, metabolomics, etc. Can we get them all together and somehow being able to find these both our unknown knowns and the unknown unknowns, as Ransfield actually was saying 20 years ago, can we actually find what are those molecules from the hundreds of thousands to millions of molecules that we know already that will be great for treating different diseases from the pharma route, or for putting them in CPG products, our food and nutrition, in order to treat more of the chronic ailments like inflammation. So this is what we're building, and this is primarily built here in Thessaloniki. And it already has brought thousands of compounds that our partners and clients have screened and validated. And I will close with the vision of a world where AI-assisted healthcare makes it more affordable, safe, precise, and personalized for everyone, leading to a longer and high quality of life. Thank you.